Hello everyone. So today we will cover a small topic in continuation to the topic we had discussed in the last lecture. So the last lecture was about the discrete time processing of the continuous time system. So where we have implemented a continuous time system in the discrete time framework. But today we shall see the continuous time processing of discrete time systems. Okay, so the idea here is that we are given the sequences xn, and this is some discrete time system which produces another sequence y of n, where you can consider the impulse response of the discrete time system as hn in the time domain and h of e to the power j omega in the frequency domain, right? So in a similar way what we had done for the reverse process, if we open this discrete time system block, what we actually want to implement this, given this x of n. So here now we shall have the discrete to continuous time conversion, which will generate the continuous time signal xc of t when I have the sampling time capital T, and there is some continuous time system lying inside this block diagram, which we have to identify to implement the above discrete time system. This will produce an output, let's call it the yc of t, and again carrying out C to D conversion with the sampling time t would produce the sequence y of n. So this is what we want to implement. Okay, so couple of points to be noticed, that generally we do not use this block diagram or to implement a discrete time system, because we have already discussed in the initial couple of classes the various advantages of processing in the discrete time framework, right? But this implementation in fact provides a useful interpretation of certain discrete time system that have no simple interpretation in discrete time domain. We shall consider one example to highlight this point, the second point. But let's see that how we can, first of all, let's see the theoretical idea behind this implementation aspect, and then we shall consider an example. So from the definition, so first block is the discrete D to C converter, and from the definition of ideal D to C converter, the information what is available to us, that xc of j omega and yc of j omega would be equal to 0 for mod omega greater than equal to pi by t. Okay? This we had seen many times earlier. Now second thing is the C to D converter samples yc of t without aliasing, because of the first bullet point. So we can express xc of t given any x of n, where the summation is from n minus infinity to infinity, x of n sine pi t minus nt by t divided by pi t minus nt by capital T. Okay. And similarly, given y of n, we can again express yc as minus infinity to infinity for the given y of n, which is basically the interpolation. Okay, where we know that x of n is equal to xc of nt and y of n is equal to yc of nt. Okay, this all information we has discussed many times previously. So I'm just writing here so that we can see that how the information is, how we can obtain the continuous time frequency response, which is the middle block. Okay? So the frequency domain relationships, now we can see that xc of j omega would be equal to t times of x of e to the power j omega t. So this relationship we had seen in the last class when we were discussing about the impulse invariance. So from the impulse invariance you can also set up this relationship between the input signals, where it is nothing but the time scale version of the discrete time input sequence. So this relationship hold for mod omega less than pi by t, right? Because for mod omega greater than pi by t it would be equal to 0. Similarly, we have yc of j omega. Note that here yc of j omega is obtained by convoluting this xc of t and hc of t, and in the frequency domain it would be the multiplication of the frequency response of xc and the frequency response of hc, that is hc. Let's forgot to write this hc, so write this hc, it's in the subscript of this h. Okay, so here we would have hc of j omega times xc of j omega. Okay, now from the first relationship we can express y of e to the power j omega as 1 by t times of y of c j omega by t. So many times we would be using this big omega is equal to omega by t there, right? And this relationship holds mod omega less than pi. So this is basically the same thing in the different x-axis omega, either in the continuous time or in the discrete time. So if I combine all these three relationships, I can express my h of e to the power j omega as equal to hc of j omega by t, right, for mod omega less than pi. So it shows that given h of e to the power j omega, you can compute hc in this way. We shall see the one of the nice aspect of considering this implementation in the continuous time domain for a discrete time system. So this relationship also says that the overall frequency response of the system, this is the overall frequency response of the system, will be equal to a given h of e to the power j omega if the frequency response of the continuous time system is, if I scale this omega, let hc j omega would be equal to e to the power j omega t for mod omega less than pi by t. Right? So this is how you can compute hc of j omega in the continuous time domain. Now another point is, since we have xc of j omega is equal to 0 for mod omega greater than pi by t, because it follows from the C to D conversion process we had seen earlier, so that no aliasing happens. So in this scenario, hc of j omega may be chosen arbitrarily for above pi by t, because below before pi by t or above pi by t we have this xc of j omega equal to 0, but most of the time we generally choose as a, or let's call it the convenient choice, that we choose hc of j omega equal to 0 for mod omega less than pi by t, right? So these are the couple of relationship to implement a discrete time system using the continuous time. So consider an example. Now we can see, we can move to the example. This is the case of non-integer delay. So let's see what does it mean. So let's say we have some discrete time system given as h e to the power j omega as e to the power minus j omega delta, right, for mod omega less than pi. So when you have delta is an integer, then you can express y of n as equal to x of n minus delta, right? This we had seen when we were discussing about the properties of the discrete time system. So this was one of the properties of the delay property. But the interesting point is that when delta is not an integer, then this relationship has no formal meaning, because you cannot shift the sequence xn by some non-integer amount, right? Because in the discrete time framework, the time index is an integer, but if delta is not an integer, this relationship has no formal meaning. So now let's see how we can take advantage of this concept to implement this non-integer delay. So let hc of j omega is equal to h of e to the power j omega t, okay? And which would be equal to e to the power minus j omega t delta. So this we have this relationship we had obtained before seeing this example. So now I can express my yc of t as xc of t minus t times delta in the continuous time domain. Okay, the shifting may not be necessary an integer, so this quantity may not be an integer, but still I can express this relationship in the continuous time domain. So the idea here is that xc of t in this block diagram, yeah, so xc of t is the band limited interpolation of x of n, for which you can use this equation, and y of n is obtained by sampling yc of t. Okay? So we had already also seen how we can do the sampling. So what does it mean? So that if you have delta is equal to pi by 2, so let's say if you have delta is equal to 1 by 2, some non-integer, then y of n would be the values of the band limited interpolation halfway between the input sequence values. So if we see the how does it look like in the figures. So this is my, let's use this different color. So this is your xc of t in the dashed dotted line, in the dashed line, sorry, and given this x of n, you can interpolate this signal, right, using that equation, using the low pass filters, right? Now in the b part, we can obtain yc of t using this relationship if we have this delta is equal to 1 by 2, and you have now obtained this signal. So once you have obtained this signal, you can carry out its sampling at the same sampling time capital T. So you have obtained y of n basically, but it wasn't possible if you directly process these two sequences through a discrete time system, because you cannot have unknown integer delay. Okay, so this was the idea, and using that figure, we can now write y of n as yc of nt, where yc of nt is expressed as xc of nt minus t delta, and xc, this relation from the previous equation we can express as for k minus infinity to infinity, from this sequence xk sine pi t minus delta t minus kt by t. So this would be your y of n. Okay, so this is what we call the non-integer delay representation. Okay. Now if I consider this equation at t is equal to n times t, I can express this as summation over xk sine pi n minus k minus delta, because your this t in the denominator would cancel out, and here you would have pi n minus k minus delta. Okay, so your h of n, so from this equation I can write my h of n as sine pi n minus delta divided by pi n minus delta for all n lying between minus infinity to infinity. Okay. So we can see from this equation also that when delta is not an integer, hn has an infinite extent. Right? And when you have delta as some integer, let's call it n naught, then in that case you can express h of n as delta n minus n naught, what we had seen above, when you have delta as an integer. Okay, so this implementation, continuous time implementation of the discrete time system, it helps in such kind of problems which cannot be dealt directly by considering it as a discrete time system. Okay, so we can stop here today. Yeah, thank you.